Now that we've learned some inheritance patterns, we can apply them and use them to solve puzzles like how a particular trait is inherited. One way to do this is with a family tree called a pedigree. A pedigree chart maps a trait through many generations, normally at least 3. Biological males are square and women are round, so those with the trait of interest are shaded. And if you have kids, a line connects you to your partner, and then all the descendants are grouped under kind of a branching set of lines. So we've got parents and children here. Now, the trait of interest that's shaded could be dominant or recessive. If you're trying to puzzle out the inheritance pattern, you won't know if the trait is dominant or recessively inherited, but you can look at the patterns in the pedigree and figure it out. So let's look at these 2 identical pedigrees. So in both cases, the parents are heterozygous, but the trees look different. In one, the trait of interest is recessive, and in the other, the trait of interest is dominant. So if you think of a trait that's known for skipping generations, those are typically recessive traits. So you can see how the parents can both be heterozygous and not show the trait, but that recessive trait can show up in the next generation. Dominant traits really can't disappear and then show up again later. They have to be, traced back every generation, or they disappear completely, at least until another parent from another lineage brings that trait back, or the trait could arise by some kind of spontaneous mutation. So you can see things can get pretty complicated, but typically a pedigree question's only going to ask you, to track a particular trait. They're not going to throw a random mutation at you. One huge giveaway that a pedigree is tracing a recessive trait is when you see these half-shaded shapes. They are shading what we call the carriers. Carrier is another way of saying heterozygous carrier. They bring the trait to the next generation without actually showing it themselves. So again, that's carrier for carrying the trait to the next generation. All right, so I'm just going to throw a big tree at us now. So you can see we've got 4 generations here. The first one, the second generation, the third, and the fourth. We have this set of siblings kind of coming out of nowhere. And then you can see all these, connections. And in this case, they don't even show the partner. They just show the offspring for that particular child of these parents. So what we're looking at here, it should be, kind of screaming in your head, this is a recessive trait because these parents do not show the trait, but their children do. And so what we know is that they are carriers. And then we can just, in this case, I don't have enough information to know which of their parents were carriers, but I'm just going to designate a set of parents so that you can watch that. Let's see, this particular parent gave their recessive allele to this parent. This individual gave their recessive allele to this individual. And so these 2 parents together gave their recessive trait to their children. So there are the genotypes to make that a little clearer. But not every genotype is going to be completely clear, right? Because these 2 individuals that have children showing the dominant trait, we don't know if they got a big A, little a, or a big A, big A. We don't know if they carry the trait to the next generation or not until we see what their children look like, right? So we'll just draw that little dash to show that we're unsure. So you can identify genotypes that way as well if you can't figure it out. A lot of times you can. So here's another pedigree we're looking at. And again, as I look at this, I'm seeing it skip a generation because it shows up here and then it does not show up in this generation. Now I know it shows up in the partner, but these parents managed to have a child that does not show the trait. So that to me says, recessive trait. And so as I work through this, I just started here and identified the recessive individuals as little a. And then in this case, we could figure out all the siblings because of this parent having a dominant allele. So they must have passed that to their offspring, and this parent must have passed a recessive to their offspring. And so from the phenotypes of these children, it's easy to figure out one or the other. So when you have one parent showing the recessive trait and one not, you can figure out all the genotypes of the offspring. And here's just some more that we can puzzle out. We know that the father must have a dominant A because he does not show the trait, but because all his children show the recessive trait, we know he must be heterozygous. And so, we can work from there and figure things out, fill in some. We know that all the children of these two parents must either, because again, it's the same pattern from before. One dominant allele and one recessive allele from this parent. This parent always gives a recessive allele, so the offspring can really only be homozygous recessive or heterozygous. So hopefully you're starting to see wow, this can be kind of complicated looking, but the patterns aren't actually that complicated. And the best way to learn this is to try it yourself, and we're going to do that really soon. But I want to show you one more example, and that is when the trait is actually sex-linked. So it's linked to the X chromosome, and it's recessive. You could have a dominant X trait, you could have a dominant Y trait, but we're not going to get into that. Recessive X-linked traits are more common in XY males because those individuals only have one X chromosome. Females have two X's, so males we say are hemizygous, they only have one X. Females, just like with an autosomal trait, can be homozygous recessive. So XX females have to inherit two recessive copies to show the recessive phenotype. So one of the things you'll be looking for when you're looking for an X-linked recessive pattern is to see if generally more males are showing the trait than females. That's a pattern you'll see. But it can be hard to tell an X-linked recessive pattern from an autosomal recessive pattern. The first thing you need to do is just find a recessive pattern, that generation skipping, and you can see it here. All right, and then you can see if mostly squares are shaded, and we do. We have, 7 squares and only two circles shaded, so that's a little off, quite a bit off balance. And then one kind of giveaway is when a mother has the trait and all her sons have it, because remember, a mother passes her X to her sons, and so if she has two recessive X's, the sons get their Y from their dad, and so all the males have the same trait their mother had. So that can be a pattern you can be looking for. So let's take a look. So if we fill in that according to the sons getting the Y and a recessive X from their mother, and we can look. So we know this mother must be a carrier because for this daughter to get two X's, she had to get a recessive X from her father and from her mother. That means that this son had to get a recessive X from his mother, but she doesn't show the trait, so she is a carrier as well. So there are their genotypes. And then we can figure out really the genotypes of all of the children of this couple. So we know that any daughter that shows the trait must have two recessive X's. The sons that show the trait must have one recessive X and a Y. And then the sons that don't show the trait would be XY. Not too bad. Again, it can seem really scary at first, but the more you practice this, the easier it becomes. And that's how you use pedigrees to solve inheritance patterns.